We see many different conditional jump. So let's see some example how we will do that. So for example, you see here, if we try to compare the unsigned value EAX and EBX. So if EAX is greater than EBX, I need to do some other operation. So that's why we need to jump to a label. So how should we do that? Is the first thing you need to comp EAX and EBX. So after the result, depends on what you want to process. So if the EAX is greater than EBX, so you will see we will do the JA or JG. But one thing is because we are considered the EAX, EBX is unsigned value, so we do the JA. So we jump to a label. So the first thing you use the comp to do your comparison. So then we follow by the JA operation. So that's you comp your EAX and with the EBX. So then you jump using the JA. So this one, the larger, just mean a label. So this one is the code label in your code. So very similar to this one, but if we consider EAX and EBX contain the signed value, so we're still using the comp instruction, but we need to follow by the JG operation. Okay, so the same thing here after we comp EAX and EBX. So then we do the JG. So the greater here, that's mean a code label. So that's the example after we do the comparison instruction. So then how we will handle the conditional jump. So the next example is very similar. So the same thing, we are trying to compare EAX. So now remember your comp instruction. You need to have at least one is registered. So earlier we have two registered, but here if you have the other one is the memory operand, that's fine. So we can compare the EAX is less than or equal to the val1. So if we want to jump, so that's what you will see. You will have J, E, so equal. So then less than, so the J, B, E. So here, because it's for unsigned. So if for the signed integer, so then we will do the JLE, because we do the less than for the sign. So let's do a little bit more now. So we want to compare unsigned AX to BX. So then which one is bigger? We will copy over the bigger value of these two registers to a variable named large. So how should we do that? So of course, you will see the first thing you need to do is you need to compare your AX and BX. So on the other hand is you do your comp AX, BX. So then we say the copy the larger one, right? So that's why here, if AX is greater than BX, so we do the JA. So we jump to the JA. So then in the JA to the other code label. So this code label, we will move the AX to large. However, we also have the other situation, right? So the other situation is if the BX is greater. So that's why here, okay, so here that's finished the first part. So we compare AX with BX. So if AX is greater, you see we jump to the next code label. So AX is bigger, so we move AX to the large. So how about the other situation? Right, so if AX is greater, we already jumped to here. But if not, if AX is not greater, we will see the jump. We will see, oh, it's not correct. So we will continue to the next line. So when you come to the next line, that means the BX is greater. So that's why here we type, you move BX to the large. We finish? Yeah, you need to be careful, right? Because you see when you do the jump JA next, Your code label should be somewhere after this move bx to large. But one thing is, if the bx is greater, I move to the large, right? Should I continue to this code label? No, right? So that's why here we need to find a way after we copy over bx to the large, I need to skip this code label. So that's why we have the other code label we call final. So this final actually is after this code label next. So after my bx is moved to the large, I will do the unconditional jump to here. So that's why we can have the greater value ax or bx move to the large. Is that correct? Right, so here is because we're using the JA for the unsigned integer. So now the same thing. This one is the example you can see from here. So the similar situation when we compare the signed integer. So then by here we will copy the smaller value to the variable called small. So you will see they will be the same thing. I still need to compare ax and the bx. But what we'll do is what? We will move ax to the small, but it's because ax is smaller than bx. So that means it's JL. That means the last because we do the sign integer. So sign integer we will think about is less than or greater than. So here is less than. So that's why here you will see this one is for the sign integer if we copy over a smaller value to the small. So if that's ax is less than bx, I jump to the next. So the same thing here. If not, I will skip this jump. So I come here, I move bx to the small. But don't forget, after we finish, we need to skip this line. So that's why here you will need to have another final as well. So here, I think the space is not big enough. So after we resize, that's why you can see here, you will jump to the final. So that's another jump example. So remember, anytime you can post the video if you have question. For now, I cannot answer you, but you can write down your question. We will go over your question during the Zoom meeting. Let's continue to do more example. So here they ask you to jump to L1. Okay, if the memory word point by the EXI equal to 0. Okay, so what does that mean? The memory word point by ESI. Right, so that means your ESI refer to the memory location, right? We use the ESI with the square bracket so that we can access the value. So that's why here the same thing, we can use the comp. So we comp the ESI. We comp if the ESI equal to 0. Okay, so here, do I need to use a pointer? Yes, I need, because you need to think about if I don't have the word PTR, when we're using the ESI square bracket only to compare the 0, we don't know the ESI how many bytes I need to read. So that's why when I compare to 0, I need to using the word PTR. So we tell the compiler from the ESI location, I need to read 2 bytes. So I compare this one with 0. If they are equal to 0, that means the JE equal or JZ if the 0 flag is set. Okay, so that's why either way we will do the JE equal, so they jump to L1. Okay. So how about the other one is the ESI, still using the ESI point 2. But this ESI value we are reading is the double word in memory point. And they are even number. How can I check the location for the ESI is even number? Post your video, think about what is the even number? Right, your even number, that means your last bit will be 0, right? So that's why here, if we will have the last bit is 0. Actually, I don't care besides the last bit. So that's why here we need to use the even number is the last bit is 0, right? So that's why I don't care any other bit. I only care the last bit. So the last bit I want to do is, remember I need to use the AND instruction. So the AND instruction with any value end with 0, they become 0. But end with 1, they will keep their original value. But here, right, I need to use the AND instruction. But I don't want to have my destination operand value EDI point to be updated. So that's why we need to use the test operation. Remember, comp and the test, they both are the instruction. They won't update the destination operand. So here, my EDI point to the value is double word. I'm using the double PTR. So then I AND, but I don't want to update the values, so I do the test. Test is the same as AND operation. So here, if this one is even number, your last bit is 0, end with 1, there still is 0. So that's why we know if this value is even number, after my test, the 0 flag will be set. So that's why, again, we do the JZ. Because 0 flag is set, I jump to the L2. Did you remember how to check even number? Okay, continue with our last example. You need to think first before you see the answer. So this task we want to do is, we want to jump. What kind of situation we want to jump? We jump to the label L1 when bits 0, 1, 3 in the AL are all set. So that's why we compare all the bits in AL. Remember, what's mean all set? Yeah, that's me. I don't care other bits. I only care the 0, 1, and the 3. These bits, they need to be set. So that's, again, remember, if you only care these 3 bits for the set, right? So that's why we need to using the AND operation. So your AND operation they will do is, they will AND with 0 clear all the other bits. But 0, 1, and 3, they will leave with the 1. So that's why we clear all other bits instead of except the 0, 1, and 3. So on the other hand, that's me this one. I need to end with my AL with this value. So then if you end with AL with this value, right, you see all other bits end with 0, they will become 0. But if these 3 bits, they are set, they will end with 1. They are also equal to 1. So since we need to have all of them to be set, so that's why later we need to compare the result. Are they exactly equal to this one? Okay, so now the first thing we need to think. So this one, should we do AND or test? Yeah, actually, unfortunately, this one we have to use the AND because we really need to see the AL value being changed. So that's why we AND AL with the bit we want. So the 0, that means all the bits need to be clear. So then when you have AL, if these 3 bits, after they AND, they are still equal to 1, we need to update this AL. So after this AL being updated, they need to exactly equal to this value. That means they are all set. So we're using the JE, jump to the L1.